Hi, my name is Sydney Huddle. I'm a major in strategic marketing with a minor in sales and a certification in data analysis. This is my Bdan 310 R code final project. I don't know how to set up my camera. This is like I've taken multiple takes. I don't know how to figure this out to where it looks like I'm not cheating, but I'm also able to read off my computer. I'm sorry if it looks weird, but to prove that I am not cheating, I have memorized all of this. I don't have any tabs open except for this one random new tab that I don't even have anything written in. I don't have anything in Word. I have nothing around me to help me. I don't even know what this is. I'm not cheating. This is completely memorized, and you can tell because I sound weird whenever I try and talk whenever I'm presenting. Anyways, environment window, console window, everything is completely cleared out. I am reading this off of my computer like this. I know that it was supposed to be like 90% my face. I don't know how to do that. Anyways, to start, we're looking at the body measurements data to begin. Read Excel and R code. That pretty much just makes it to where R code is able to read Excel. Run. Then we have library caret. This just makes it to where it's able to split data into training and testing data, is all that it does. Run it. Library R part. That makes it to where it's able to run decision tree models, regressions, ANOVAs, anything like that. Run it. Body data, read Excel. This is pretty much just telling R code to actually read the Excel data for the body measurements that we uploaded for Excel. And then as you can see, the environment window, environment window is just pasting all the information that R code learned from doing that. Anyways, set seed. That is just making it to where every single time that R code is run, it's copying and it's looking at the exact same testing variables every single time. It's not changing. It's just consistently making sure that it's always testing the same thing. Index. Create data partition. A data partition is pretty much just splitting the data into testing and training variables. For this, you can see it says 0.7. That means that the training data is going to be the 0.7. I'm sorry if I'm looking up. I just stared at a blank wall. There's nothing on the wall. That's how I think. The training data is going to be at the 70%. That's where the 0.7 comes in. And then testing data is going to be at the 30%. That's all that the data partitioning is looking at. Run. This is creating a data set for the training data at 70%, the trained data. And then the testing data, it's doing the same thing, just at 30%. It's just creating a data set. That's all that those two functions did. Now we're creating a linear regression model. We have LM. That's looking at things like body weight, height, age, all those things. And we're creating a linear regression model through this. And we're building one, pretty much. So now we're taking a linear regression model and we're telling it to make predictions because it's an equation. That is what the linear prediction is doing. So now we have linear MRSC, linear MAE, and linear R squared. That's taking the linear regression model and creating results for it. For the MRSE, MAE, and the R squared. All this is also showing up in the environment window. I don't know if I even pointed at the right thing just then. Anyways, so for MRSE, that's pretty much just saying how far off are the predictions on average. For MAE, that's saying how many errors do we have each time. For MRSE and MAE, we want lower values, not higher ones. R squared is saying how statistically accurate this regression model is. So we do want a higher number for R squared, but not for the other two. Anyways, so we're looking at that for the model. All the results for that go into the environment window, but we're going to change it later to where we're able to compare them easier. Next, we have a decision tree model. This is for our part. So that's pretty much doing the same thing. It's just another model that we can compare. And again, it's looking at the exact same factors. Does this one use ANOVA? I can't remember. It doesn't say. I don't remember. Anyways. So yeah, we're going to run that. Did I click the right button? I have no idea. I can't see, man. So now we're taking that linear model move over here because you can't see my head. The linear model, and then we're now making predictions from that decision tree. I keep saying linear. The decision tree has now looked at all the different things from the Excel file, and now we're asking it to make predictions. Cool. Now we're on to the tree model, MRSE, MAE, and the R-squared. Again, MRSE, we're looking for the lower value. It just means how off are the predictions on average. MAE is for how many errors that there are for the decision tree model, and we also want a lower value for that. R-squared is for how statistically accurate the model is, and we want a higher value for that. All those results then pop up in the console window. I can't read that right now, but yeah. So now we're looking at the linear results. We're telling it to pretty much group it into a table for the linear regression model. And then tree results, asking it to group it into a table for the decision tree model. Run. Results, we're asking it to bind it together so that way it's in one table so that we're able to compare them easier. Run it, and then print results. And so as you can see right here, that just printed everything out to where we're able to compare it easier. I'm going to flip the computer towards me so I'm able to read it. The linear regression model for RMSE has 4.37. For decision tree, it has 5.17. Linear regression model has a lower RMSE. That's better. The MAE, 3.55 for linear regression. For decision tree, 4.30. The MAE for the linear regression model is lower. That one is better. The R-squared for the linear regression model is 0.689. For the decision tree, it is 0.570. We're looking for the higher value. The higher value is the linear regression model again. In other words, looking at all of that is pretty much just to say the linear regression model was the better model. It is a better fit for this kind of data. Not to say decision tree is always wrong. It just works better in the case of this situation. So that's body measurements. We're done with that. Now we are going to look into loan data. We're going to start up here at the top. A lot of this is, again, repetitive. We have the read Excel function. Just makes it to where you're able to read Excel. Or our code is able to read Excel. Run. Then we have the library caret function. Just makes it to where it's able to split the data into test and training data variables. Run. Then we have, I forgot what it says, library R part. That's pretty much just making it to where it's able to run models, regressions, ANOVAs, whatnot. Run it. I do this every single time because I know that technically you don't have to. It just makes my brain feel better to do it step by step so there aren't any weird funkiness. Anyways, loan data. We're just telling our code to read the actual Excel file for the loan. Run. Names, I did this personally just because I wanted to be able to see and for you to see what all the different variables that the loan is actually looking at is for. So things like marital status, income, what else is on here? Self-employment, dependents, things like that go into loan approval. It just helps my head. Anyways, then we're looking into the loan data results as a factor. Am I reading that right? I guess it's just organizing it into a categorical factor because it is things like yes, no, approval, denied, whatnot. So we're going to run that. I think I just skipped something else. I'm so sorry. Set C, that's just splitting the data the same way every single time. It's just making it to where it is consistent. Things are getting split the same way every single time. Run that. Index, create data partition. That is just splitting the data again into testing versus training. The training is going to be at 70%. That's where the 0.7p comes from. And then the testing data is at the 30%. Run. Train data and test data, both of those functions just create data sets at the 70% level for the training, 30% level for the testing. So we're going to run both of those. We're creating a logistical model. There's a word in between there. I don't remember what it is. This is interesting because it uses the GLM function, but this is pretty much looking more into an equation rather than any functions or anything like that. We're building an equation pretty much with this. For this, it's binomial. The reason why we're putting binomial is because it's using things like zeros and ones, because they are more categorical rather than numerical results. So that's just pretty much assigning a number for that. Anyways, run. Where am I? Oh, so log probability, predict, test, response, type equals response, whatever. This is pretty much just saying everything that we just pulled from the logistical model. What is the probability for everything? So what are the numbers that are being pulled after running all of that is, I guess, the best way to describe it. Next, we have log predict. So this is taking all of those probabilities and then turning them into actual predictions that we're looking at, and to be able to better understand and better be able to compare. Next, logistical prediction factors. This is just organizing it and assigning it with categories. The factors means categories pretty much for the approved, not approved. It's just cleaning it. Next, we have log confusion. That's because we're making a confusion matrix. That's pretty much just a way of being able to compare models with the results, looking at the basis of, wasn't looking at anything, I was looking at my hand. Accuracy, sensitivity, specificity, which we'll get more into later. And so we're running that for the logistical model. So now we're creating a tree model R part, and this creates train data and whatnot. It's the same thing as body measurements. It's just using the if function. If this means this, and that then creates the result of this, I think. Then we have tree prediction. We are taking the results of the tree model and actually making predictions with it. It's just kind of narrowing down the data and just cleaning it. So those probabilities, let's turn it into predictions pretty much. Run. Tree confusion. We're making another confusion matrix. It's the same thing as for the logistical model. It's just turning things into accuracy, sensitivity, specificity. Again, getting more into that later. All of this is also showing up on the console window as I run it, and you can test it for yourself on our code whenever you grade this. Run. So now print logistical confusion and print tree model, decision tree model confusion. So now we're gonna look at the results. I'm gonna kind of like move you around if I can, so you can see-ish better, I guess, and so I can read better. Okay. So the thing with accuracy, sensitivity, and specificity is they each mean something. Accuracy is the most important because it pretty much is saying how many times did the model get it right, or the regression, or whatever. How many times did it get it correct? Then you have sensitivity, which is saying how many times were the approval correct? How many times was agreed correct in this sense, because we're looking at factors of 2 or binomials or whatever. Specificity is for how many times did we get denied correct. So then looking at that. So that's just for, again, binomial, yes, no, approved, not approved, whatnot. So now we're looking at the accuracy for, the accuracy for the confusion matrix for the logistical model. For the accuracy for the logistical, 0.8395. That's how accurate it was. Scroll down. For the other one, for the decision tree model, it's also 0.8395. They are the same. That's great. Then for the sensitivity, for the first one, we have 0.4286. For the decision tree model, we have, I believe it is also, 0.4286. They are, again, the same. Specificity for the logistical model is 0.9833. We scroll down again. And for the, I don't like saying the other one, for the decision tree model, 0.9833 again. They got the same results. That's great. Both of them worked just fine. There was probably another one that could have also been tested, but these were the two that I chose to test, and they just got the same results. But here's the bad news with it that I also know. With specificity and sensitivity, you want them to be comparable, but you also want them to be balanced. So with specificity, meaning they got most of the answers for approval denied correct, since that was like at the 0.9, I believe it was, that means that it has better chance of approving something wrong, or getting a loan denied correct. I'm over 15 minutes, I'm so sorry. Versus sensitivity, which is the opposite. So the sensitivity was lower. I believe it was at around 0.4. That means I was less as good at predicting approvals and if they were correct. So you want them to be balanced. So neither one of these models were great. They're unbalanced and they could be better. But anyways, everything is saved in Posit Cloud. You can run it yourself. I have the files down here for the body measurements and the loan applications or whatever it's called. And yeah, thanks for listening.